and welcome everyone. It's recorded anyway. And computational fluid dynamics is a very important subject. And I want to just go to the next slide and give some background. Because in the integrated delivery project, which is a very important requirement, not just in the AIA, it's worldwide, in all the architects unions and engineering unions, is that we have always a master file platform where all the data, all the simulations end up in. Right? It's very important. And here you see, let me get the sketch. Where's the sketcher? Here you see all these products, in engineering and architecture, all of them. So what we use for years, decades at FIU is the Autodesk platforms, the Flow, which was expired in 2014, but students still love it to use it because it's very simple and you don't have to do coding of the ISO 7730 and ASHRAE 55 standards for exterior and interior. And and then we have CFD done for many years, and it's all integrated in the building information modeling workflow. And so does CATIA, so does Siemens generative design, SolidWorks, and so on. All these products. But the major challenge is that once you're finished as a student in academia, and that applies also for faculty and staff or researchers, and you need to continue with CFD somehow. There's no open access platform for that. It's not cheap. It costs a lot of money. So, and here comes in Open Foam Butterfly that will be subject today because it's an open. Let me close this form software. So, as you all know from 5612 and 5621, we need to have a baseline. The baseline is for our climate zone. It's a Saffir-Simpson scale, and it goes from tropical depression up to category 5. We need to respect that when we design buildings, public spaces, interior. Think about natural ventilation. Remember, the higher you go, the higher the wind speed and the pressure. It's all about pressure. And with that, all the pollutants and water, etc., comes into the building or pressures on the building. Now, the question is, if we go indoor, then we use mostly thermal comfort standards that you learned about. And it's also part of the licensing when you take the NCARB. You learned about 7730, the ISO standards, which is widely used worldwide by over 90% of the world population. And then we have the American version, which is ASHRAE 55. Now, this also applies for the exterior. And today we will show those, in particular for the exterior. There's another 4 or 5 hours workshop needed to go into the indoor. So don't be surprised. And how do we start? What I know from my part is, of course, the Autodesk and Cove and Sapphire area. So you have to go to the weather station, and you do the same in Rhino. And if you have an EBW file, that's the one you use. And then you look at the wind roses, the season, and the schedules where you need to run the simulation, because you need to define the parameters and the boundaries. If you don't do that, then you work on a CFD for over a year because you can do all kinds of simulations. So you need to define first the parameters and the boundaries. And with this comes then the materials, etc. Now, the easy part is then in BIM software like CATIA or Archicad or Revit or other Siemens, is that you have CFD integrated. So it's part of that master file. It's not a separated island. So whatever you simulate goes into the environment of that data processing and optimization. So it's integrated and it's shared in on a platform with all the other engineers. So we're all sharing the same data that we are simulating, so we can work on these parallel. So, for example, this is the new version 2021. It takes 2 minutes to export it into or run it into CFD. Then it goes to the fitness test, the model assessment, and that took, for this model, took 6 minutes. But the science behind this is accurate and patient work, that all the definitions of mass floor, mass ceiling, mass enclosure, etc., is correctly coded. Otherwise, you won't get to the service levers, you won't get to the part gaps, or the model gaps. It will identify it immediately. And then you have to go back and fix it. And that's true for all the other packages. And then you have to wrap it. But wrapping means you have to wrap the model, and I'm sure the Open Foam workshop will go into details deeply. And then you have the wind tunnel. So this is the wind tunnel. This is definition. And you can only create a wind tunnel if you know what you want to test. You need to know the wind rows, the wind data. Where's the wind coming from? What's the speed? And then you have to click. You have to go through mesh sizes, motion groups, and define all the materials. In this wind tunnel, if I click on this, you can make it transparent, and you see then the high rise. So we need to know those baseline parameters, even for the exterior and even more for the interior. So this is very important. And then you have to go to the material editors and understand what is viscosity, conductivity, specific heat, emissivity, wall roughness, etc. So this is work. Now, you can also go from Revit directly into Fusion. So you see here the Fusion environment, or Autodesk Inventor, or Autodesk Nastran. These are the more detailed modeling platforms where you calculate the U and R values, you create the details for a facade system of the materials, and you go through all the fitness tested as they refer to building codes and UL ratings here in the US. Because if you develop details for facade, you need to apply all these thermal stresses, structural loads, etc., and then run it to computational fluid dynamics. In this case, in Inventor and in Nastran and Fusion, Autodesk offers ANSYS, access to ANSYS. ANSYS is a very expensive software, but it has more capabilities than the Autodesk version. But then you can go really into details, and you can also use generative design, do optimization, topological, genetic, algorithmic scenarios, which cost cloud points. So you have to pay for the cloud points. So that brings us to the Open Foam workshop, and I'm stepping out now here because, again, I think Open Foam and Butterfly with Ladybug and all these opportunities is very important to integrate now in the BIM platform. Since we have Rhino 7 in Revit, we have so many more opportunities now we did not have 10, 20 years ago. So this is fantastic. Theodorus, it's all yours.
Yes, thank you. Thank you. That's an excellent introduction, Thomas. And thank you so many of you that came here today. I hope that what you see, you both understand and kind of excites you for the future. I'm going to share my screen very quickly. And I will do a bit of, let's say, lighter introduction when it comes to what this is and what I will show you today. And I call this playing the whole game. It's a sort of like gentle introduction to Butterfly as much as I can. And I've done this presentation, or I've started making this presentation years ago. And the reason that it's still viable is because it's focusing on concepts, let's say, and not really on state of the art of the technology. So I will try to share some of my thoughts about CFD. And okay, first of all, the Ladybug tools is a collection of tools that do many different things, right? This is a very nice slide by Chris and Mustafa. And we will be dealing with Butterfly today that deals with airflow modeling, right? Computational fluid dynamics. And there are ways to couple all this. And we won't have time today, but hopefully maybe in a future workshop, we can see how you can go further and start to couple these different studies, right? And just some really ancient history. So this is kind of how the Ladybug tools, started around 2013, the first release. I started getting involved somewhere here before 2015 with computational design. And about 6 months later, I asked the forum, the very active community, what can I do? And I had a couple of points that I was marginally okay with, and one of them was CFD. And Mustafa was very, very, very happy. We restarted the whole project, a few people, and we started making Butterfly. At the end, it was just the two of us, and it came out around here, around in the middle of 2016, an alpha version. And for the next half year and even more, all we discussed about was how to install OpenFOAM and Butterfly. Unfortunately, it wasn't our fault, but it was a big difficulty, something that is now solved. And I won't show it today, by the way, but I will try to discuss a bit how to do it. And yeah, so this is kind of like the history, and the official release was somewhere after 2017. I'm sorry. And, you know, unfortunately, in the beginning, most of the issues I said were about installation, but also Butterfly provided some very nice features. And this is what I will try to show you today and a bit explain what the purpose behind at least my thinking of building Butterfly was. And my inspiration was this book by David Perkins called Making Learning Whole. And in this book, he uses this metaphor of playing the whole game. So he says that a very nice way of teaching and actually learning is to think of it as a game. And as a game, it makes immediately sense to everyone, right? And every time we get better at this game, we like it even more and we appreciate it and we go deeper and deeper into it. And playing the whole game involves not just figuring out how to solve a problem, but, you know, understanding what is the problem in the first place. You know, why do I want to do this? What does it solve? So it's all about curiosity, discovery, and creativity, and a bit of camaraderie, and I will explain what that means later. And the issue here was that CFD wasn't really about these things, right? CFD is a very difficult, you know, we all know, and if you talk with the CFD experts, they will tell you, it's a very difficult subject. Most of them have PhD in physics to understand it fully and develop code and do things. And it's considered very hard for architects or any designer to do without being an expert, right? And this is what Butterfly is meant to sort of overcome. It's meant to democratize and allow everyone to use it in certain degree, right? To design with the wind in a way. So this is the playing the whole game, and the examples he gave was actually kids playing a game, and you don't give them a book about how to play baseball, right? They just play, and then a few sessions later, they know how to play the game. There is an intuition to it, right? So we don't need a book and a description for everything. And so how do we let everyone play? First of all, we create something open source and collaborative, right? This is what Laidback Tools was, and Butterfly is a part of it. And then we try to make it accessible as much as possible. Again, Butterfly was built with that in mind, to make these studies that are very difficult a bit accessible, you know, hiding some of the complexity, right? And also to, you know, to do it because, you know, it works, right? We need to do CFD and design with the wind because it actually works. It actually gives benefit both to your designs and to you as designers. And I can attest to that because when I started, I didn't know CFD. And after learning how to do CFD, I can actually think of design differently, right? So it actually works. And the biggest, you know, also face and a big issue that the industries will have to face, right? Which is the talent gap. I feel more and more young people decide to do something else, even after they get an architecture degree, right? And, you know, in this way, if you let people play and explore and experiment, you know, you will bring more of them back into the fold in a way. And of course, how to inspire, right? Hopefully this is slightly inspirational for you. And hopefully when you do it yourselves, and if you do it, you will see that it can inspire you to make some sort of a difference, right? So this way we can let everyone play with everyone. That's the goal of Butterfly. And of course, the community of peers that we are developing, that's the way to do it. So what was the vision for Butterfly? So there is this relationship between us and the tool, right? And the way I understand it, there are different levels to it, right? And most of the CFD happens at the validation level. This is where the experts come in, right? CFD engineers, they really need to validate, as Professor Spiegelhalter said, you know, there are specific requirements we need to make, and you need to validate. This is absolutely correct, right? But design is also about exploration, and that is partly happening, not too much, still by experts, right? Because if it's very difficult to even validate, it's even more difficult to explore and experiment. Then there is a bit of academic and industrial researchers doing some of the experimentation and exploration, right? But then we are lacking the understanding, and this understanding comes, I think, from that playing the game, right? Comes from interacting with the thing. And many designers have a problem to interact with CFD, and it's a valid problem. It was very difficult for me when I started. It took months, and I had someone to guide me as well with it. And it took months of painful, let's say, process to understand. And And yeah, there is some interaction between these two, but I think we need to do more. So these were the main goals of Butterfly: bring experts into the fold. So we were hoping to actually bring CFD engineers and use it, make it better, improve it, right? Expand the people who do it, all architects and designers. You know, there's no reason in my mind why a landscape designer shouldn't be able to do a CFD and understand how to place outdoor landscape, right, in architecture. And also broaden the scope of the studies, you know, so do more things with it. So that was the main goals. Okay. And okay, I'm sorry about this break, please. So now, if I can, because we don't have so much time, I will go directly to Butterfly, if that makes sense. And I've prepared, okay, so I will show you this because it might be a bit scary at first, right? It's a typical Grasshopper spaghetti thing. I try to keep it as little spaghetti as possible. And what I wanna show this for is that I wanna tell you a couple of things. First of all, I want to say that this is a sort of sequential process. You can see it here. There are certain steps to it, right? And certain steps you can never avoid. Some you can possibly skip, but it also makes it a sort of logical process, right? There are requirements to be met at every step and going forward. The other thing that I want to show with the script is that it is almost absolutely reproducible. So when I share it with you, and I will share it with everyone today, that means that about 90%, and this is my own kind of number, so I don't want to be legally bound to it, but about 90% of the cases you will ever try, this script will handle very nicely for you. It will run all the best practices that we have implemented. It will create a study, a simulation, and your results will be more or less correct. But so that said, though, in order to properly understand how to use the script, I wanted to discuss today about what it does and what is behind it, rather than tell you where is this component coming from and what is happening with it, right? So this is how we start. Bear in mind, we don't have too much time. So this has a bit of disclaimers. First, we are focusing on outdoor studies, outdoor wind simulation, right? There is no indoor here. All the volumes are closed, right? We are doing, some buildings and wind around them. And, they are simplified, we call it isothermal, let's say, circumstance where, temperature doesn't play a role in a way. It's just wind, it's just the wind effect. So everything is sort of simplified, but still this applies to almost all outdoor studies, even in practice, in my projects, this is how it would be. Okay, so let's start. The first step, as you can see here, is, as always, like Professor says, is to localize our study, right? And review the conditions. So this is very important. And I would say that about 50% should be here, right? These few components. What does this mean? First, we need to find the weather file. How do we find the weather file? I use this site here. It's the APW map, but there are many other sites, right? And what I did is I just searched for Florida, United States, and you can see here already, actually, if I zoom out, there's a few weather files in Florida. If I go to Miami, there are a few of them again, right? And you can select, this is the DOE file, the Department of Environment, I believe, and this is the climate one building org file, which I tend to use. These are a bit more updated. So if you want to choose between the two, choose this, right? And I chose the airport file. Usually in cities, and this is quite interesting, you can find weather files in the cities. These are interesting, but they are not always good for this sort of studies because you can imagine the measurements that are already sort of polluted by the buildings, right? So we go to the airport usually because there is an open area. It's a sort of, not very turbulent flow, right? This is why we try to calculate that. So what we do here, I'm sorry, you don't need to download. You can simply copy to your clipboard, right? And this is what I did. And then I brought it here. So if you paste this, you will see the same thing that I have here, right? You just get this file. And then Ladybug will take care of everything. It will download the weather file for you into a location that you want. This is the download weather component, which is quite, and I wanted not to show too many about components. We don't have much time, but it's in the 0 import here. So it's actually the first component here, the download weather, right? And then what we do is we parse this file with this component. We import the data, essentially, right? We have an import EPW component here, and this parses and gets you all the different data that you need. And in fact, what I do is I use the wind speed and the direction to make a windows. And this is what the first thing that you should check, right? To understand, okay, should I do a CFD simulation? Yes. And when should I do it? What is the direction, the wind direction that I should care about, right? And this component tells you all of this, and I will show it right now. So if we go to the top, and I really didn't want to show this. It's because Yeah. So you can see here, and this is the weather, the wind direction and wind velocity for Miami City, let's say, right? And you can see a very clear pattern, right? The biggest frequency of wind comes from the east. It's very clear, right? And also the other thing that you can see is that, you know, the highest wind velocities tend to come from the sea as well. So this sort of nexus here from a bit before east and a bit before south is where you want to focus when you're designing for natural ventilation, and also north and northwest. So you see that there is a sort of two-direction importance, right? So if you were designing a building and you wanted to do natural ventilation, and in that case, you really want to capture a cross ventilation, you really want the wind to cross through your building, right? You would imagine some orientation between those two, right? Something that captures at least one of the two. So this is like a very rule of thumb without even simulation. What should I do? How should I orient my buildings? Okay, and how do we make use of this? So what I tend to do is when you tend actually to run a CFD simulation, you don't really run one, right? You run multiple of them, and you actually select the dominant wind directions. What that is not very clear, right? It depends on the scope of your study, the time you have, the money you have, the computational resources. In the real world, it will be almost defined by others than you, right? But usually I would say I would never do less than 6, something like that, a rule of thumb, right? And usually you can go all the way up to 16. And the most I've done is 36 wind directions, which I think is an overkill. We did it because it sounded nice. So 36 would mean that you have 36 different wind simulations, and your building is oriented in a way that captures that wind. So northeast, all these 10-degree intervals, right? So in this case, what we can do, it's not very important what this is. It just gets the dominant wind directions, depending how many they are, right? So you can select here how many you want, and it will identify it for us. So here, we are grabbing the 8 most dominant wind directions from this weather file with this vanilla Grasshopper stuff. And we can see here that is 0, 70, 90, 112, as we saw, from a bit above east all the way. And if I show it like this, maybe it's going to be better. So you see that 0 is quite high, 67 is here, 90 is here, 112 is here. So it captures the eight most dominant, right? And why do we need that? Because as we will see, and as Professor showed earlier, we have a wind tunnel, and the way Butterfly at least creates the wind tunnel, you need to orient your building appropriately according to this input wind direction. So the wind tunnel is not a circle, as you may have seen in other cases. It's not a circle where you can change the direction of the wind and you keep your mesh the same. Instead is a rectangle like we saw before, and we need to orient the building, to rotate the building, right? And how do we do that? Well, we don't want to do it manually, so we use Grasshopper to do that for us. So I will skip a bit this madness here, and I will go here. So we use a simple rotate component, and we take care of that information to input it here. So before we pass our geometry to Butterfly, we take care to rotate it appropriately, right? And I will show you how. So that's the first 2 steps. Understand the local climate, and then select your wind directions, sort of frame your study, right? Which usually, as I said, is framed by others for you, by other things, let's say external. The third is to bring some sort of geometry, right? This is anything you want. It doesn't need to be parametric. I did this here because I thought it would be fun, but it can be a simple box, a couple of masses, a whole city, right? It can be a detailed design coming from Revit that you absolutely need to clean up before you do CFD. It can be anything, right? It can be something you design by hand, right? It can be anything you want. What I did obviously here is I made a twisting tower because I think it's very, very on point here to do. And actually I created my own version of this Agora garden that you know from Taipei, I believe. It's a very simple version, of course, because I did it in let's say 1 hour, and they had a bit more time. But I will show it to you. And I think it's a nice thing because it also will let me talk about meshing, which is very important, and strategies for meshing. So this is my version of the Agora Tower. Again, this can be anything. And apparently right now is nothing. I'm sorry, let me zoom in. Okay, of course, because they're not. Okay. So this can be anything. And in this case is this building here that you see, right? And what does it have? It has a simple core here at the center. It has some, rotating apartments here with green. and it has a nice balcony going around the building in this bluish color, right? This is our building. I wanted to do this because, first of all, it looks a bit funky and maybe it's interesting. It's also a bit complex, so we can discuss about meshing, and also to show you that you can do anything. You can try to simulate anything, right? It doesn't have to be a simple volume. It's very good to start with a simple volume. So if you wanted to investigate the potential of a twisting tower, I wouldn't start like this. I would start with simple masses, twisting masses, right? No like curved and linear stuff. But you can also do very detailed design. So this is an example, right? And of course, we won't run the simulation today because we would need a few hours to watch our screens, but we will prepare, right? Okay, so this is the geometry, right? And it can be, as I said, anything. It could be a box, and Butterfly will take care, whatever you give it, it will automatically, almost automatically create the CFD case for you. So you don't need to worry about, this building is much bigger than my previous iteration. Should I change my design, my CFD settings? Butterfly will do that for you. In fact, this is why Butterfly was made, right? Okay, so once we have our geometries, so these B-reps, right? And once we make sure, it's very important to be closed, right? Because we want, because I will explain a bit why that is important, but they need to be closed and valid geometries. Then we do what we always do with Ladybug tools, and if you've done any Honeybee, you will know that. We create butterfly geometries, which is just a sort of, different format that Butterfly understands and can propagate to the other components to use it, right? How we do that, we have a Butterfly create butterfly geometry component, right? And we plug in our geometries inside, and they are created, and they become butterfly geometries that can then be meshed, be created as a CFD case, right? And as I said, it's very important, before you put them, if you do this, it's not necessary that you do this, by the way. You may want to investigate just one direction, so all this complexity is not necessary. But if you want to use the dominant directions, then you use this angle here, right? You use the appropriate rotation, and you pass it to the component. And as I will show you now, the component will take care to sort of do it. In this case, the first dominant direction is 0. So we haven't done any rotation, right? Because this is already one of the dominant directions. And just bear in mind, the wind in Butterfly comes from the bottom. Always the way I'm looking now, it comes from the bottom and it moves upwards, right? This is my standard best practice. You can change that if you want, but it might confuse you. But if we were to do the second direction, for example, and I can change it here, if we just select the second wind direction, you will see the model twist appropriately. It will take a few seconds because actually in these seconds that you see past, it has created a fully fledged CFD simulation ready to run. And that's it. That's the whole CFD simulation. That's the time it needed. And you see now that it has twisted a bit, and I can show you that this is true by... Actually, I cannot show you because, okay, I can show it through here, yeah. So you see that it has twisted. So this was our original geometry, and it has turned 67.5 degrees, which was, it just happened to be our second dominant direction, right? So Butterfly has now the appropriate input inside, right? Okay. So then why did I choose this type of model? Because it allows us to sort of discuss about meshing, and meshing is probably the most important thing you should learn today. And as you can see, we have color-coded different things, and we also have equal butterfly geometries. And why do we do that? So I'm sorry about the sound. Today is everyone's birthday, if you know. It's Chinese New Year, so you will hear a bit of this. I'm sorry, I apologize. So as you can see, I have followed this separation as this color coding also in butterfly geometries. And the reason we do that is because these butterfly geometries are called regions, right? And when we try to mesh later, and right now actually, we can, if we split our input into different regions, we can mesh with different properties each region. And this is very important, right? This is very important because, for example, maybe these apartments, they don't need so much detail, right? But maybe this more complex here balcony needs more detail. So it needs to be refined more. And I will explain what this refinement is in a second. So this is how we can achieve that. We can create different geometries, right? And for each geometry, you see this input here, we have a different refinement level, right? And we can play with different values. For example, here, I've put this value here, which is just one, refine once. That's what this says. And if I wanted to do the balconies a bit more, I might put here 2, refine twice. And I will explain in a second what this means. But this is what this allows you to do. And now it's taking a bit because it's actually refreshing the whole case. And this allows me now to refine only this surface more, right? It allows you for this sort of differential, approach to meshing. Okay, what is this refinement? I will skip a bit ahead because it's necessary to understand meshing. So when we start meshing, we have something called a bounding box. The professor showed that, right? And I will show you the bounding box now that Butterfly makes. And it's right here. It's already made, by the way. So this is the bounding box that we made. It's quite big, and it should be. But it shouldn't scare you because the way we mesh, very, very little thing, most of the cells that we will have will be where we care about. So this is the bounding box we have right now, right? It's actually, I would say, not big enough, at least in this distance. I will explain later why. And when we make this background mesh, you can imagine this as a Lego, right? You can imagine as a Lego split in very small cubes everywhere. And let's say that each of these cubes is 10 by 10 by 10. Let's say that all this size, it starts at 10 meters size, right? I will use meters, or maybe say like, 40 feet, 40, if you want feet. And so this is our initial background mesh. So what does refinement means? It means that where every level of refinement means that it takes that initial box, right, of 10 by 10 by 10, and it divides it in half. So imagine from 10, it goes down to 5, right? So if I refine once, it means that I divide my whole mesh in half. So from 10 meters size, it goes to 5, right? If I refine twice here, from 10 meters, it goes to 5, and then one more is 2.5, right? So this is the simplest way I can explain refinement. It's simply halving the size of the cells that our mesh is going to be made of, right? And I will go back to the presentation to explain this a little better. And additionally, what Butterfly offers us is a component that is quite useful that creates these refinement regions. What are these refinement regions? Always, we don't really care about all these bounding box, especially, since we have only one building here, we don't really care what happens out here, right? We don't need so much refined mesh here. We need our refinement to be closer, right? So we can define regions. And my best practice with Butterfly, because we have another component that I will show later, my best practice is to use this distance refinement mode. And I will explain now, if I can, with Rhino, actually, what this means, right? What is the distance refinement? Let's say that we have a little box here, and actually it's very big, that we want to refine. And we want to refine the area around it, right? It's very important for us that around this area, we have more refined things. What can we do? Well, we can say that take this surface here, and in the first 5 meters, let's say around it, or like, let's say 10 meters, right? From this side and from this side, and if I can offset, can I offset surface? I don't know if I have an offset surface here. Yeah, so if here we say, right? So what we say is we can tell OpenFOAM to, from here and 10 meters outwards, right? Imagine it as a bounding box extending, refine more than what you do outside of here, right? So let's say that inside here, we do 2 refinement levels. It means like we refine our mesh twice because we want this to be more accurate, right? We care because we will have pedestrian areas and we care about this to be more accurate. And then what you can say is you can take this one, you can say, okay, now, I'm sorry. Then you can put more levels here. So you can say, okay, now outside of here, so we have another box here, and I will put them on the side so we can see. So around here and around this box, refine twice, and then around this box, refine once. And imagine this box is overlapping. I just broke them out so that we can see them, right? And maybe I should have done wireframe so that I shouldn't do this. So let's show them like this. So these are the areas. So essentially what you're making is you're taking your geometry here, and you're making these volumes. And inside those volumes, you sequentially, you refine less and less and less. And this is very important because you want your meshing to be gradient mesh. It's called a gradient. You want the jumps from one area to the other to not be very big. And this was a big problem when Butterfly first came out, before we made the component that I will show you later. people had, let's say, 1 meter mesh around the buildings, 10-meter mesh directly after. And then everything would diverge, nothing would run properly, right? So this logic of doing it stepwise, in a stepwise manner, keeps things correctly. How do we do this? It's very simple. In this component that has the distance-based refinement, these steps here are exactly what I showed here, right? What does this say? For the first 10 meters around my geometries, right? Refine twice, right? This is what it says, right? For the first 10 meters, refine twice, right? And then the next one is for the next 20 meters, this is actually 10 meters. So at the 20 meters, refine once, right? And you can do as many as you want here. So I can actually come here and say, okay, you know what, you just do, okay, it doesn't really make sense to have 0 here, but you can do it like this, right? You can put more. So if you had like 3, 2, 1, you can do like that. You would refine 3 times, 2 times. So you can add as many as you want here, right? Just bear in mind, the more levels you add, the more cells, the more time, the bigger computer and all this stuff. We will discuss the limits in a bit. Okay, so this is the first step. So we create butterfly geometries. Very simply, we just put the geometries here, and we can put refinement levels here according to how important these geometries are to us, right? You can also not refine here. I always kind of refine once, if I'm honest. That's why I have it here. This is my best practice in a way, right? So this is what I want to show you today. I refine once and then twice if the geometry is very, very important to me or very complex. And then you can also assign the distance-based refinement, and you can, the geometry you put here, you know, kind of like defines what is refined. So for example, if it's the balconies that you only care, you might connect the balconies here. So you refine, you know, just around the balconies, right? If it's the whole city or block that you care, you put all your buildings. So you decide what that is, right, in a way. Just remember the logic is like this. So outwards, stepwise manner. Okay, so after we have the geometries, and I just realized these are not connected. Interesting. Okay, this was the problem. So I'm sorry, I will just pause the solution for a second. After we have the geometries, we create the wind tunnel like Professor showed, and we do that with the wind tunnel component. And the wind tunnel is a bit of engineering how to create it, right? And now I want to go back to the presentation to just discuss a bit about this, if possible. So what is the logic behind creating a wind tunnel? So this is what we call the domain, right? So to design a proper boundary, we need to relate the dimensions of our domain. So you can think about it as a rectangle here, the length and the width, with the geometries that you're using. So this domain always flexes and changes size and shape, depending on what the geometries you're using are, right? And I will explain why. So the first thing that we care about in order to calculate this is we get a bounding box of our geometries. So imagine in here, you have whatever you design. It can be a small city, it can be a small block, it can be one building or even a small bridge or just, you know, a panel from a facade, it doesn't matter. You just get its bounding box, right? And then this is a sort of best practice, right? It is kind of industrial best practice. You can find, I will share later a link, but it's also my best practice, right? Then what I do is I extend the sides of my domain by this bounding box. So here we symmetrically extend, right, this domain by one of these boxes. Imagine like you move this box one to the right and one to the left, right? This is a sort of rule of thumb you can do. You take the bounding box and you move it right and left, right? So symmetrically. And then you also do the same on the windward area. We call it windward is before the building, right? Before it hits the building. Why is this distance smaller than this distance, right? Is important because when you're doing a sort of validation or outdoor study, you have a specific input velocities, right? And a lot of the times when you're doing certification, for example, those are defined by the tool, right? So you want the velocity that comes to your buildings, you want it to be as close as possible to those values. So the smaller distance it will travel, the less it will be affected by your domain, right? That's the reason why we do it. And the reason why we have this extension much bigger, so I will go one step more. The reason why we have this extension much bigger, the leeward extension, is because we need to let the wind settle. So after it hits our building, there is a lot of turbulence, the wind goes up and down between our buildings, it has a lot of complexity. And after it escapes, and this is open area, we want it before it reaches the end of our domain to be completely settled. And almost at peace in a way, right? We want the pressure here in a way to be zero, but we don't define it. We want it to converge in this way, and for that to happen, you need to give it a lot of size, a lot of space, right? And so how do we decide this distance here? My rule of thumb is this distance from here to the end is 5 of these boxes. So 5 bounding boxes. So imagine you take this box and you move it 1, 2, 3, 4, 5, right? And what this means is every time your geometry changes and this bounding box adjusts, your domain has to adjust. It has to be bigger if your building is higher, right? If you have a very high tower, you need to give it much more space to settle, right? To converge. And it can be smaller if your buildings are less, right? So this is sort of like how we design the bounding box. Symmetrically on the left, on the right, and behind. So these are the same size, right? And then much bigger distance on the leeward side. And more important to understand, because Butterfly will do all this for you, is why. We do it because it needs to converge. It needs to reach at the position it converges. And you see this here. 1 geometry length and 5 geometry lengths, right? And then, the rest is 1 and 1. This, of course, has edge cases, right? You will find, for example, if you're doing a big township, right? A lot of houses spread across large area and all of them are very short, you will notice that you will need, Butterfly will make a bit of smaller domain that you need. So there we need to manually adjust. So as I said, 90% of the cases will work out of the box. Some other cases we need a bit of adjustment, right? Okay, and also the H-max, again, best practices, typically is around 5 times of the maximum height you have. So if the maximum height across your 50 buildings is 90 meters, you need to have at least 450 meters height at your sites, right? It's typical something like that. A bit better way of doing it is to calculate what is called the blockage ratio. And how do you do that? Imagine you take all your 3D buildings and you squash them on this surface here, on your input surface. Imagine you project all the buildings to the surface, right? And then at that surface, you have 2 areas. One is the building area, the opaque, right? And the other is the air area, it's open. And that blockage, as we call it, needs to be at least 3%. So not more than 3%. So you need to have 97% of this let's say, vertical slice open to the wind. So this is another way that is usually more accepted in a way to do this blockage ratio, right? And okay, and we adjust things accordingly. Okay, so this is the first thing I want to say. Again, you don't need to do this manually, and I used to do this manually because Butterfly will do this for you, and especially this code. So we have here a component that creates these tunnel parameters, and you can see here I have the windward before the geometry, leeward after the geometry, sides, left and right, and top, how high, right? And I have my best practice here. What I have is my own native script that is not very beautiful, but it takes care to take all your geometries. If you had more, you would put more. And it calculates this for you. So it calculates these extensions, right? And this is the result that you see, right? This is the result here. I need to apologize. I need to run the solver again. And by using this component, this makes it automatic. So automatically it has adjusted based on these best practices, our wind tunnel. So if I look at it this way, you can almost see how it's 5 times higher than the building, right? And, in this case, we only have one building. That's why it looks a bit short. And in this case, this might be an edge case. Although you will almost never have a simulation like this. You will always have context, right? But this could be an edge case in the sense that I think it might need more extension. Yeah, this is an intuition you will get after running studies, and you will see if they have converged or not. So, okay, so this is how the wind tunnel happens. There are a couple of other inputs. One is the name, and you will see here they have a concatenate component. What is this? This is if we want to make a parametric CFD, right? Parametric, so what do? We make a name, in this case, Agora Garden, okay? And then I also add here the input direction. If you remember here, these numbers that define the wind directions, right? Because I can iterate through them and create different cases to run, I also use this value as the name so that my cases don't get overridden, right? So that you create a new name. That's the whole idea. And lastly, we put a wind vector here, a wind velocity, right? As I said, I always use Y+, so it always goes upwards here. It always goes from down to top. You can change this, but at your own peril in the script, right? It's a bit hard-coded right now. And the wind speed, of course, is the appropriate wind speed from the weather file. So this always needs to be here, right? And finally, we have this value landscape. I won't go very deep into it. It has the biggest tooltip you can find in Ladybug Tools, right? You can read this. And this is the value you should put depending on where your buildings are. If you're near the sea, not a lot of buildings, you need to put like 0 or 1. If we are in a city, typical city center is between 5 and 6, right? This defines how rough your landscape will be, right? And how much it will affect the wind velocity, as I said before it reaches your building, right? This sort of simulates the urban environment that we can never model around the cities, because we can never do a whole city, right? We will always cut a small part of the city. So this sort of tries to simulate the effect these buildings would have that you're not simulating, you're not designing explicitly. So this is the second step, the fifth step, as I see, of creating the wind tunnel, right? And again, this will happen automatically. So I will show you later how when we change the input, this will change automatically for you, right? But it's good to understand why this looks like this. This is what I try to do. The next step is setting up all the parameters of our keys, right? And we start with meshing, then we do some simulation parameters, and we even do some runtime post-processing. This is sort of my addition to Butterfly or to these scripts. The most important component, I think, then the best component of Butterfly is this component here. It's called gradient mesh, wind tunnel gradient. And this, for me, was the most important because it was something that I used to do manually. There was this manual calculator. I can share it later if you're interested to play around. And I had to do it for each case. So if you wanted to do 36 wind directions for each different wind direction, you had to do 36 manual calculations and all that, but no longer. So this will do it for you. And what this does, I will show in the presentation in a second, but it's very important. So, and it really makes simulations with OpenFOAM much more efficient, right? And much more efficient and more accurate, actually. And I will go back to the simulation to discuss about what this is. And again, I think it's important to understand, even though you will never do it manually, to understand what happens in the component, right? So as I said before, we have a background mesh, right? This is a wind tunnel. This is the Lego I was talking about before. This is a slice, but you can imagine this is a 3D volume, right? And let's say a normal mesh of some size, I don't know, this is maybe a kilometer, I don't know what it is. If you start with 5 meters, which is a very typical start, and in fact, when I was doing projects in Singapore, this is the minimum they require you to start, right? Everywhere, you know, at the edges of your wind tunnel, let's say. If you have a 5 by 5 by 5, for this domain, you have about 400,000 cells. It's not a lot, right? It's not a lot. But let's say that you want in your buildings to have more refined, right? You want to have 2 meters, right? Or 1 meter. So how do you do that? Well, one simple way is to say, okay, you know what? Divide everything more and have 2 by 2 by 2, right? Because this is in 3 dimensions, immediately we have an explosion of cells. So our background mesh, this refined mesh, from 400,000, which is something okay, very fast actually for today's computers, it goes all the way to 6 million cells. Even without buildings, right? This is empty. We haven't put anything yet. So as you can imagine, this doesn't scale very well. It's not a very efficient way of doing it. And why is it not efficient? Because we really don't care what happens here, as we said, right? We make the bounding, the domain, big enough so that we don't really care the size of these cells. We just care that their neighbors are not very different. There is a gradient increase, but we want them to increase. We want them to be much bigger here than what they are where our geometry is somewhere here, right? How do we do that? We do it with a gradient mesh, right? And what is this gradient mesh? Is this here, exactly. So what this does, it says, okay, if my building is here, okay, just make a small bounding box, and I can define it myself manually, right, around my buildings. And inside here, make everything one meter cell. So make everything just 1 by 1 by 1. And then outside here, outwards to other directions, just increase these cells by 15%. At each step, the next cell is 15% bigger. So the first cell is 1.15. The second is something like 1.25, you know, 1.4. And of course, this is a geometric progression, like it increases quite fast, right? You can see at the end, we have a cell that could be 200 meters. It doesn't matter at all. As long as this cell is far away from your geometry, right? It doesn't matter, it's in fact efficient. And what we did here is we actually increased our background mesh refinement compared to this one. We went from 2 meters to 1 meter around our geometries, and we decreased our total cells by a factor of 10. So this makes it very, very efficient, a very efficient way of doing it. Other models, like the ones that Professor Spiegelhalter explained, other software, sorry, and especially meshing software, have even better strategies, right? They have something that's called unstructured mesh, which means that you can have different cell sizes at different areas, and they can be, you can see it if you Google ANSYS, you can see it that it has like a sort of unstructured mesh where different cell sizes, they go according to the needs of the mesh, right? Unfortunately, all this software, especially the meshing software, are the most expensive, the most expensive of the workflow, right? And the only open source meshing software that I know that does quality control is SnappyHex, the one we're using here, and is a structured mesh. And the best way to do this refinement in structured mesh is this gradient mesh. So we are using the best, let's say, means possible that we have right now, at least, and hopefully this changes in the future. So by this little trick, we can generate this, and I won't discuss about this now. We can generate a much more refined mesh with orders of magnitude less cells. And this is what this component does. And it has a few inputs that you can play around with, and you see it. The first input, the very important, is the cell size. So this just asks us, what is the refinement you want to have around here in the center of this cross that you just saw, right? In this case, I have 4, right? This is up to you. It depends on the size of the geometries you have, what you want to simulate, and all these things. Then it asks for the cell-to-cell ratio. So it asks you, how much do you want me to increase at each step? This should be less than 1.15. This is the best practice. Most people use 1.1. 1.15 is the maximum jump you can have. The best practice should not go above this, and it should be less, right? Then another important input is the wake offset, which means, okay, I won't just refine around the building, because after the building is a very complex area of wind, right? So I will give a bit of area like this. So the wake offset means how far away from the building do you want me to refine? If it's like 5 meters is here, 10 meters is here, 50 meters is here, right? So it extends this refinement by how many meters you say here, right? And it's good to give something relative to the building height, right? In this case, you can even give a whole building height here as a best practice, if you have the computational means to do that. If the tower is very big and is 150 meters, this wake offset, this thing here will add a lot of cells, but it's worth it if you want very accurate simulations, right? And the last offset is the height. Somehow, because this happens on 3D space, right? All this refinement is in 3D space. We also have a height offset. And here, you can put something that makes sense to you. I usually put 10, 15, 20 meters. We don't really need so much more above, I think. But okay, it depends again on the time you have, the scope, computational means, and everything. So with these options, right, this sort of best practice and logical options, you create this gradient mesh, right? And this is what these components do. And I will go later and show you this, how this happens, right, in action, right? And after we're done with that, this also gives us the total cell count here, which is interesting. It's good to keep in mind, right? So this is the total cell count of our background mesh. This doesn't include any geometry yet. Our building, our Agora building is not meshed yet. It doesn't exist, right? And we have 450,000 cells. That's okay. For urban studies outwards, it makes sense with the computers we have today, right? I should say that 1 million cells, you should have, let's say, a bit over 1 gigabyte of memory, right? It's a very, very plain rule of thumb. I would say if you want to run, let's say, a 10 million cell simulation, I would have at least 16 or 12, because you also have Windows or Linux where you run it. You have other things running. So the rough rule of thumb is that, like 1 million, 1 gigabyte, right? Which is okay today. Most of us have a lot of memory, but if you're doing this in a laptop, just bear in mind that maybe you have some restrictions, right? The next step we do is we give some options for how to refine the geometry itself, right? And this is what the SnappyHex, if you notice, all these components are called dicts, right? This is a SnappyHex mesh dict. Why? Because Butterfly, it's not really, it's making dictionaries. It's making open form cases in the format that it does. And I will show you in a second what we made in 5 seconds that this took to run, right? I will show you in a second. So here what I do, one of the problems that we had when we first came out with Butterfly is, and this was my mistake, is that I gave an example file like this, and then I never added this thing here. Will explain where it was. And what I had is a very simple design, right? And I had a max global cell here that it was just my choice, like 1 million cells, if I remember correctly, right? And then people started playing with this initial definition, and they did okay. They took away my simple box and they put their neighborhood, right? And they tried to mesh it, and all of them came to the forums and said, you know what, I'm trying to mesh, but I can't see anything. And the problem was this max global cells here. So this max global cells means how many cells OpenFOAM will allow you to create, right? So if your geometry, your initial geometry is very complex and your background mesh is very big, and this number is very small, it won't add anything. So for example, we have 451,000 cells, right? If this number was less than this, let's say I put it here, 400,000 cells, it would literally won't create any building. Why? Because it will start meshing and it will say, okay, I start meshing. Step 1, 451,000 cells. Oops, more than maximum allowed. I stop meshing. So it would literally stop meshing directly without doing anything. And this is what happened to most users. So to fix this, I have a rule of thumb again, but this you can adjust it of my own. And I say, you know, take this background mesh, multiply it by 5, right? And use this as your max global. So this is, it makes it a bit parametric, right? So if you put like a simple building with a small domain, this is a small number. If I had like hundreds of buildings here, and this was like 3 million, this would be a 50 million. So this is a rule of thumb, of course. Always be careful of that. But the logic is that you need to give it enough cells that it can do its work. It can start meshing and capture the geometries, like Professor was showing before, the wrapping around, right? It doesn't mean that it will use all of them, right? It won't. So you can give, if you want to be safe, you can give a very big number in the limits of your RAM, right? And SnappyHex will just stop before that, right? It's okay. But it will stop before that if you don't give enough, and it might not even create the geometries, right? So this is what this does. It sort of takes care of that, right? All the other options are default, and Butterfly does this very well. It has very well default values. I don't need to explain them. I will explain what they do, these two of them, because you can play around, but you don't even need to worry about them, right? This value here, the between levels, it just tries to make the cell even more gradient. If you remember, when we go from one cell to the other, we have a small jump, right? So this just puts intermediate cells in between to make it more gradient. Imagine like a staircase, and you put more steps to make it easier to come down, right? But this also adds total cells. So the more this is, the more cells you have, the less cells. And this surface feature level is something that I always put by default here almost too. And what it does, it takes the wireframe of your geometry and just takes care to refine around it. And that is important sometimes because it captures the shape of your mesh better, right? But even without this, if you had this default, never change it, it will work, right? The other thing here is we just tell it to run in parallel. Of course, CFD should be parallel. Here you can put the number of CPUs you want to give. I would always leave like a couple of threads, or don't use everything, but depending on how many you have, 64 or 32, OpenFOAM will take care to use all of them, right? And at the end, here we just create a mesh dictionary. That's it, the SnappyHex mesh. The other inputs I said, the solution parameters, I won't go very deeply into it. This is the physics of CFD, right? Here we just tell it, and this is a mistake here. Here we just tell it, you know, when to stop going. So every time CFD runs an iteration, it has some residuals, the error, imagine, of the calculations, right? So here I've told it to keep going until you reach 10 in the -5 of residuals. It's a very standard best practice thing that people do. Some people might do much more, depending on the case, right? But for outdoors, I think this is very good. You might never reach it, if I'm honest, with this sort of meshes that we do. And here are all the different parameters. The U is velocity, P is pressure, K and epsilon is the turbulence parameters, right? And not is some other parameter for roughness, yeah. And the other input here is, which is very important, this is how many iterations to run. Here I have it 1,000. This should never be 1,000 for proper CFD, but if you're doing a quick CFD, 1,000 is okay. When I was running urban studies, typically 5,000 to 6,000 iterations. It takes a while. CFD is a very long process, right? And then another value that I typically use, and I tell everyone to just leave at this is the purge right. CFD will take care, OpenFOAM will take care to save the results every few steps, right? Let's say every 100 steps. But if you run 5,000 iterations, that means it will save 50 times. And these files can be very heavy. They can fill your hard disk very, very quickly. So here you can tell it how many to keep. Just keep the 2 latest. That's all this does, right? This is a way to keep your hard disk from flooding. That's all it is. And that's it. These are the options. You can run all your studies, for example, through this course, I'm pretty sure, without changing anything here. You don't need to change anything, right? Butterfly is very good to make this by default for you. And I will talk about these surfaces later in a bit. The last step is to run and forget. Forget is literally forget, because this takes a lot of time, right? And I need to warn you, like CFD is not for the impatient, right? Even like a very small study, you know, like this, it might take hours. If you do like a few 100,000 cells, it will take hours, right? If you do a proper few million, tens of million cells, it will take days. This is why, if you remember, I had this, the motivation to develop infrared. So, okay. So what we do here, I always use realizable from the models we have. This is a runs model. So it means is not a transient, it's a steady state simulation. It means we are really simulating a moment in time. This is how most of the outdoor studies for example, wind comfort or even natural ventilation happen, because we simply cannot do a transient simulation for all the different wind velocities we will encounter in the year, right? So what we do instead is we do average wind velocities from the windrows, as you remember, and we sort of extrapolate that later if we want to make an annual study, right? We say, okay, during these hours, we have this velocity, so just multiply it and put it in the whole year. I won't discuss about this. If we have a workshop about comfort, we can go deeply into this. Realizable I like because it converges faster than all the others. I either use this realizable, there is another one called RNG. I think those two are the best. You can leave this as it is forever, not care about it. But just to know what it is, it's the, let's say the model, the physical, let's say mathematical model that solves these equations, right? And all the rest is automatic. Butterfly uses some best practices for all this stuff, so you can leave it as it is. And that's it. And then we have the solve component. So as you noticed, all this, I had it all run, so everything was a true, and it took 5 seconds. What does this mean? CFD doesn't take 5 seconds. Instead, it means that I didn't run a CFD, but I created a CFD. So if you see here the components, except from this that has run, I have the true on write and not on run. If you want, and for most of you, I would suggest if you want to use Butterfly in this script to run simulations, to actually run it in here. If you put it here, something will pop up and it will create a block mesh for you, the blue form, the blue CFD that we said to install, that we will show you how to install. And then if you do it here, so this will take maybe a couple of minutes, the meshing will take maybe a couple of hours, right? And the other will take a couple of days. So I won't do it because personally, I run them differently. And I also wanted to show you what Butterfly creates. So in this 6.5 seconds, and the rest were milliseconds, let's see what we created, right? Let's show you very quickly, because I think it will lift a bit the veil on what is going on in the background. So this is, Butterfly will always save it at your user directory. It will create a Butterfly folder, and inside here, it saves things, right? So what do we have here? We have a few studies. What is the 068,158? Is the wind direction, if you remember, the angles from 0, right? And let's go inside and see what it made. So it has made these folders, and I think I need to do larger icons, maybe not so larger icons, medium icons, okay. So let's do extra large icons. So it has created these folders here, these files. The 0 folder, which now is populated, has all this open foam specific options you need to put, all your boundary conditions that you need to do. So for each surface inside, for all the wind tunnel surfaces, for your geometries, all the stuff that you had to do manually before, Butterfly has done everything for you. It also has the initial conditions of your wind profile. So this is not just one wind velocity, it's a whole logarithmic wind profile, right? It's one different wind velocity at different heights. All this was done automatically for us, right? By Butterfly. We don't need to care at all about it. The constant folder, it has exported the geometries we care. So it has exported our building. This is our building masses, right? And it has exported the refinement, and I will say in a bit what this zip-plane is, right? The refinement is this geometry that went to use it to do this refinement. We discussed the distance. And if I open this STL, I want to show you what these regions mean. Do you see this solid here? I don't know, is it visible to everyone? I hope it is.
Yes, yes.
Okay, you see here we have solid balconies, right? And if I search by solid, and we have solid balconies, it might take a while because this is a very big file. It has, I don't know, 1 million lines, but we have another and solid balconies. So this is our first region. Remember the first butterfly geometry, our balconies, right? If we go next, we have, I'm not sure why it doesn't go next. Ah, okay, sorry. This was a mistake I did before. Let me go to the other case. This case should be okay. Yeah, I think this case is okay. So because before I didn't have connected everything. So this solid here, solid and solid is the regions we discussed before. So I will find and solid, then we have core, you see solid core. And if I go to the next one, it has solid apartments. And these names are the names I put in Butterfly, right? If I go back here, this is apartments, core, and balconies. So whatever names you put here, how many regions, Butterfly will put those in an STL file and will split it into regions, because this is how the meshing will happen at different regions later. I just want to explain what that is. You don't need to care too much about it later. So these are all the physical properties, transport properties, all the turbulence, everything set from us, and the polymesh is empty. This is where the mesh will happen when you finally run these things, right? And as I said, you can run this in here. So let's try and run it. And I didn't try it. I didn't test it before, so I hope this runs. We can say run here, right? And actually we failed. Let me see why. Okay, I will fix this in a second, but it runs. So I will show you how we can do it. So when you install Blue CFD, and again, after this session, I will send the instructions. When you install it, and it's very easy to install, it's just an executable, you download it and it installs. You can right click here and this option will be available to you. It will say open in Blue CFD core terminal something, right? And if I click, you can click this with any folder, it won't do anything. But if you click it in a folder that has the open form structure, it will open something like this, right? So it has something like this. And I want to show you in terminal what happens so that you understand what happens behind Butterfly. And also to show you that what Butterfly does is simply like the biggest part of Butterfly is not to run the case, is to create all these files. All the rest is just running simple commands that I will share with you. And after this workshop, I will also update this Grasshopper to make these commands automatically for you. So you can run batches of how many cases you generate. So this is a parametric CFD Grasshopper file. I will also add the ability to generate the run script for you. So you can run them and really forget them, have them for a week, right? But let's see what it does. So the first command that we do, the first component, and I will open it here, is this block mesh. So the first run is in the component called block mesh, right? And very conveniently, the command is actually block mesh. So right now I'm writing open form commands, right? And what Butterfly runs in the background. So if I press block mesh here, it will start popping up some numbers, and very quickly it will generate something, right? And after you do open form for a while, you will start reading this and understanding what this is. And I can show you the important stuff. It shows the size of the cells here. And the other thing is here, you see 451,000 cells, right? As Butterfly told us before, this is our background mesh. So now, very quickly, and it took 1 second, we created this background mesh. And let's go see what it is. And I actually have load one here. And this is the mesh that we created. And if I load it in ParaView is a visualization program, is open source, very powerful. We need another workshop to detail how it works, and I will share some videos about that. But for now, let's assume that we opened it, right? So we opened the case, and you can see that Butterfly indeed did what we told it to do. It created a gradient mesh. You can see how big the cells here, up here. And if I zoom inside, this is our geometry, and you can see the bounding box almost around it with these 4-meter cells, right? And what you can see as well is from the tip of the building, for 50 meters after it, this size is still the same. This is the wake offset we had, if you remember, right? And the other thing that we do is Butterfly automatically does a sort of best practice on the Z, which is quite nice, I think. And you can see it here. If I a surface with edges. Oh, no, here, I'm sorry. If I do a surface with edges here, you will see it. So Butterfly also generates a mesh. This is, oh, I'm sorry. This is a bit fortunate if you do outdoor studies, a bit unfortunate if you want to do other stuff, because this is made for almost comfort studies, right? And what it does is it creates few small cells at the height level, the human level, and then it sort of slowly in a gradient manner increases these cells, right? And it does it in three different regions. One is the first 2 meters above the ground. We make sure to have like a specific size of cells. Then it goes from there all the way to the maximum height of the building, and then somewhere here, and then it just increases more upwards, right? And again, we do this to capture closer to the ground, better the flow, right? As a best practice.
Theodore,
Sure.
we have to switch to Professor Finlayson.
Oh, I'm almost done. I think I'm almost done.
Yeah,
this is
okay.
Okay, I'm almost done. So yeah, I have to apologize for this. It's really condensed for all the things that I wanted to say, but I just want to show that what we created just now. I won't go through the other commands. I could type them for you, but Butterfly will run them for you, right? And if it doesn't, we will debug it. But I just wanted to show that when you run, this is what Butterfly does in the background. It simply tells OpenFOAM to run this command, right? And the last thing I will very quickly say is that we can also do a very, very smart runtime post-processing here. I will share with the script with you how this happens and what I did here. And this is, I think, quite nice because it saves so much time in real projects. What I did here, and I show you this last thing, is I wanted to assess wind conditions at all these balconies. So I actually created these surfaces at all the balconies here. So you can, not this, of course. These are the initials. So if we rotate them, so I created all the surfaces. If you can see here, around at the mid level of the balcony, right? And with this small native Grasshopper, Butterfly exports them as STL, and then while you run your case, during runtime, it will save velocity values here. So when you come back, you can simply load these values, even in Rhino, and they will come colored with the wind velocities and everything. And I will share the scripts later. I think this is very powerful. It saves me a ton of time in post-processing. The last thing I want to say is that this script that I showed you, actually 2 things very quickly, is exactly the script I use in practice. So I'm absolutely confident that you can take it, and maybe, in a year, if you do your own projects in the real world, you can use it, right? I use it in practice, of course, with a few edge cases. It really works. It's really reproducible, and this is the power of Butterfly. And before I close, the last thing, as I said, this doesn't make sense. It's one building. So what do we want to do? We actually want to put it in the world. So I have used here Urbano. I don't have time to show you how. It's quite easy to load it, but I also have loaded the whole city. So here's the context, right? And what you can do very quickly, and I want to show this before we close, right? You can add this context, and I will add it lazily right now here, but you can add it as a new butterfly geometry. At this point, I will add it lazily. So let's say we add it to the core, and Butterfly will refresh everything, right? It will rerun the calculations, and it will create a new boundary domain with all the properties, taking into account this context. And this is the last thing that I want to show you, that any different geometry you put it, all this will adjust automatically, right? And now you can see, actually, the problem here was that this is not flattened, and we created 2 cases, I'm sorry. And so now it's taking the context here, and hopefully in a few seconds, it will create the new case. And with that, I will close. This is what I want to share. That is, this script works and is really reproducible. You can add you can rotate, you can enlarge, you can design new buildings, and it will work. And I really hope it works. I didn't practice it before. I'm not really, oh my goodness, I didn't flatten. Okay, I'm really sorry. Okay, now it works. So yeah, that's the idea. And you can see the boundary domain changes and everything adjusts. Sorry, yeah, it's done. And that's what I wanted to add. There it is. Okay. So you see how the domain adjusts.
And
you're welcome.
we will add together, then we do the editing for the tutorial and
Sure.
provide it to all students in D9 and 56.
Sure. Thank you. And I'm sorry, I know it's difficult to follow through this, and I urge you to rewatch it. It really will need much more time to condense a lot of this practical stuff, but I hope you got something, and I hope mostly that this script will help you reproduce it. And of course, we are always here. Thanks.
Awesome.
Thank you, everyone. We're
Thank
leaving
you guys.
now.
Fantastic.
Do another Zoom. Thank you so much. No? Bye-bye. Bye-bye.
Bye-bye.
Take care.
Thank you.